Record. All right, welcome everybody. So let's get started. It's a pleasure to welcome our speaker today. It's Pavel Shumyatsky from the University of Brasilia, and he is going to tell us something about commuting probability for subgroups of a finite group. Pavel, please.
Okay, thank you. Thank you so much. Thank you for the invitation. I will share the... Okay, commuting probability for subgroups of a finite group. So given a finite group, what's the probability that two random elements commute? It's easy to answer this question. We just need to take the number of all commuting pairs of elements from the group G and divide it by the total number of such pairs, which is of course the order of G square. And this number is usually called commuting probability of G, or sometimes it's also called the degree of commutativity of the group G. This is a well-studied concept, and in the literature one can find rather many publications dealing with this. Some results are about what is the set of possible values for commuting probability, and others deal with the questions of what is the impact of the commuting probability over the structure of the group G. Just to give a few examples, maybe the most famous results in this area is the so-called 5/8 theorem that says that if G is a non-abelian group, then necessarily the commuting probability is at most 5/8. If the commuting probability is at least 6/8, then actually it must be 1. And the bound 5/8 really happens when we consider non-abelian groups of order 8, either quaternion or dihedral group. Other interesting results is that is a result due to Dixon, who proved that if G is a non-abelian simple group, then the commuting probability is at most 1/12. And the result of Bob Guralnik and Jeffrey Robinson, it says that if the commuting probability is at least 3/40, then G is either soluble or it is of the form A5 times T, where T is an abelian group and A5 is an alternating group of degree 5. Okay, these are all just examples of results in this area. And the general theorem about the structure of groups with given commuting probability is due to Peter Neumann, who in 1989 proved that if G is a finite group in which the commuting probability is at least epsilon for some positive number epsilon, then G has a normal subgroup T such that both the index of T in G and the order of the commutator subgroup of T are bounded in terms of epsilon only. So in other words, this shows that if the commuting probability of the group is high, then the group has a really big abelian section. And when a group has such structure, for brevity, we will say that G is bounded by abelian by bounded. Now, if K is a subgroup of G, we can also ask what is the probability that a random element of G commutes with a random element of K. And then the answer would be, again, a fraction where in the numerator we have to take all the commuting pairs of elements from K times G and divide it by the total number of such pairs, which is the order of K times order of G. This, we will call it the commuting probability of K in G. And sometimes this is also called the relative commutativity degree of K in G. This is also a natural concept, and there are rather many papers dealing with it. So the result that I would like to talk about was obtained in a joint work with Luisa De Tomi from University of Padua. And it says that if G is a finite group having a subgroup K, whose commuting probability in G is at least epsilon, then there is a normal subgroup T in G and the subgroup B in K, such that the index of T in G and B in K and the order of the mutual commutator subgroup T and B are all bounded in terms of epsilon only. So in particular, actually, Peter Neumann's theorem can be obtained from this as a particular case when K is just G. Now, K here can be just any subgroup, not necessarily a normal subgroup. And then, of course, this commutator subgroup of T and B also in general is not normal. But it's well known that such subgroup is always normalized by both T and B. And since T is a normal subgroup of small index in G, it follows that this is a normal subgroup of T. And so while this subgroup is not necessarily normal, at least we know that its normalizer is really big. So it's almost normal. And so I would like to make a few comments, some technical remarks about this proposition. So as I mentioned, this commutator subgroup of T and B in general is not normal. But it's important to note that even if we take just a normal closure of that subgroup, N is all the order of N is also bounded in terms of epsilon only. Why? Because the commutator T and B is normal in T. And since T has a small index in G, it follows that the normalizer of that subgroup has small index. So there are only boundedly many conjugates of that subgroup. All of them are normal in T, so they normalize each other, and therefore their N is just the product of boundedly many factors, each of bounded order. So N has bounded order. And another remark relates to the case when K is normal. In the proposition, K is not necessarily normal, but in some important cases, K actually is normal. In that case, we can say something more. In particular, the subgroup B can also be chosen normal, while the subgroup T can be chosen in such way that it intersects K by a subgroup of the third term of the upper central series of T. So this Z sub 3 of T is the third term of the upper central series. So why is this? First, why B can be chosen normal? We already know that the normal closure of the commutator subgroup T and B has bounded order. So first we apply the proposition, and we choose T and B just as they are given by proposition. Then we take B naught to be the normal closure of B. Since K is normal, of course, B naught is also a subgroup of small index in K, and now it's normal. And it's easy to understand that the commutator of T and B naught is again contained in N, which we already know of small order. So really, we can just replace the original subgroup B by B naught, and therefore, without loss of generality, when K is normal, we can also assume that B is normal. And now maybe it's more tricky to understand why T can be chosen in such specific ways that it intersects K by the third term of the upper central series. But consider the normal series in the subgroup K. So K is normal subgroup, N is normal, and B is also normal now. We know that the order of N is bounded. We also know that the order of the quotient K over B is bounded, just because B has a small index in K. And therefore, their normalizers have a bounded index in G, just because their orders are, these are normal sections of bounded order. And now let's look at the centralizer of the section B over N. Actually, not difficult to understand that the subgroup T centralizes B over N because N, here is definition of N. When we kill N, it follows that in the quotient, T centralizes B, which is now normal. So T centralizes the quotient, the section B over N. And therefore, our original T, we can just replace by T, intersect with the centralizer of N, intersect with the centralizer of K over B. And in that case, it's easy to understand that the intersection of K with T would be in the third term of the upper central series of T. Just because N would be in the center of this new subgroup T, B would be in the second term and K in the third. Okay, now about the proof. The proof of the proposition is somewhat technical and really not nice to talk about it in the seminar, but there is at least one tool used in the proof that really deserves some mention, to be mentioned here. It was also used in the proof of Peter Neumann's theorem. Just I'd like to recall that a group G is called a BFC group if all conjugacy classes of G are finite and have bounded size. And it's easy to check that if every conjugacy class in the finite group G has size at most M, then the commuting probability of G is at least 1 over M. Of course, if all centralizers are big, then there is good probability that once you choose two random elements, they centralize each other. And so finite BFC group provide important examples of groups in which the commuting probability is bounded away from 0. And actually, Peter Neumann's theorem, its proof shows that these examples are not just particular examples, but actually they have rather generic nature. And in particular, Peter Neumann showed that if commuting probability of the group G is bounded away from 0 by epsilon, then G has a normal subgroup K of bounded index such that the sizes of conjugacy classes in K are all bounded in terms of epsilon. So this subgroup K would be a BFC subgroup of G. And this nicely combines with another theorem also established by Neumann, but not Peter Neumann, rather Bernard Neumann, of course, who was the father of Peter Neumann. And that's a famous theorem of 1953. It says that if the commutator subgroup of a BFC group is finite. And it follows that if all conjugacy classes of a BFC group G have size at most M, then the order of the commutator subgroup G dash is bounded in terms of M only. Bernard Neumann actually, I think he didn't, in his original paper, he didn't say anything about possible bound for the order of G dash, but then a bound was found by Jim Weigold, and then there were several other results improving the known bound. Also, of course, Peter Neumann worked on that. Okay, why I mention all this? Our result with the Louise de Tommy also based on several recent theorems in the spirit of Bernard Neumann's BFC theorem. In particular, in a joint work with Glaucia Dierings, who was my student in Brasilia, we deduced a BFC type theorem for commutators. We proved that if M is a positive integer and G a group in which all conjugacy classes of commutators have size at most M, then the second derived group is finite and has M-bounded order. Just as usual, a commutator of a group is just any element of the form A inverse, B inverse, AB for suitable elements A and B. And the commutator subgroup, of course, is a subgroup generated by commutators, but in general, elements of G dash need not be commutators. So this theorem cannot be immediately deduced from Bernard Neumann's theorem. That was really something different, and also its proof is much longer than Bernard Neumann's theorem. Well, then this result was used in some other results of this type, in particular in a joint work with Louise de Tommy, Guram Donadze. Guram Donadze is from Tbilisi, Georgia, Marta Morigi from Bologna, and myself. We deduced the following results that provides a criterion for a group to be finite by nilpotent. So here gamma sub k of G stands for the term of the lower central series of G. So we proved that if K and M are positive integers in G a group such that every element of G has centralizer in gamma sub K of index at most M, then the next term of the lower central series of the group has a finite and Km bounded order. So in particular, it follows that G is bounded by class K. Class K means nilpotent of class at most K. And this extends several classical results of Baer and Neumann. In particular, Bernard-Neumann's BFC theorem can be obtained from this, just taking k equal 1. Okay, and a BFC result of somewhat different nature was obtained in a joint work with Christina Acharya. And this says that if M is a positive integer in G group, here G can be any group, can be infinite group. A group having a subgroup K such that every conjugacy class of an element from K has size at most M. Well, and let H be the normal closure of K. Then the order of the derived group, H dash, is finite and bounded in terms of M only. And that, of course, is a kind of far-reaching generalization of Bernard-Neumann's theorem. Well, when H, or even when K is just G, we get Bernard-Neumann theorem, BFC theorem. Otherwise, it's was really different result. And this was crucial in the proof of the probabilistic result. Just I quickly explain why this is important in the probabilistic context. In general, suppose we have a subgroup K such that every conjugacy class of an element from K has size at most M. But I mean conjugacy class in the group G, not just in K. So what is the commuting probability of K in G? This is the number of commuting pairs from K times G divided by the total number of pairs. And so if we fix X in K, how many Ys we can choose to get a commuting pair? Well, of course, it's just precisely the order of the centralizer of X. So this number can be written as the sum of the order of all centralizers over all elements from K divided by the order of K times the order of G. And so here we have order of K summands, and then we divide it by the order of K. And of course, this is the average, inverse of an average of the index of the centralizer of an element from K. And just it follows easily that with these conditions, necessarily the commuting probability of K in G is at least 1 over M. So it's bounded away from 0. And the proof of the proposition actually shows that this example is not just a particular example, it's a rather generic case. Okay, but that's, I think I will not talk about the proof anymore. Instead, I will talk about some applications of this result. We didn't even call the result theorem because it's kind of really very technical proposition. And interesting cases happen when K is some kind of important subgroup. Like, for example, a verbal subgroup or Silov subgroup of G and so on. So we'll talk a little about probabilistically nilpotent groups. So in general, a group is nilpotent, so of class C, if the corresponding term of the lower central series of G is contained in the center. So what if we relax this condition and only assume that the term of the lower central series of G has high commuting probability in G? The result is that in this case, G has a nilpotent normal subgroup R of nilpotency class at most C plus 1, such that the index of R in G and the order of C plus first term of the lower central series of R are bounded. So we obtain here that the group G is bounded by class C by bounded. And it's easy to understand that Peter Neumann's theorem is a particular case of this result if we just take C equal 1. Okay. And in the same spirit, we treat the case where a K is a verbal subgroup corresponding to a word implying virtual nilpotency. So if W is a group word, we write W of G for the corresponding verbal subgroup of G. That is a subgroup generated by all W values in G. And the group word is said to imply virtual nilpotency if every finitely generated metabelian group G where W is a law, being a law means that the corresponding verbal subgroup is trivial. So every metabelian group G where W is a law has a nilpotent subgroup of finite index. There are many words of this kind. In particular, the power word x to the n is of course implies virtual nilpotency because just a metabelian, finitely generated metabelian group of exponent n, of course, it's finite, so it has a nilpotent subgroup of finite index. What is less obvious, every angle word is also implies virtual nilpotency. This is because by result of Carl Grunberg, every finitely generated soluble an angle group is nilpotent. Actually, we don't even need an angle group, just even unboundedly angle group. Finitely generated soluble angle group is nilpotent. And there are many other words that imply virtual nilpotency. And there are several important characterizations for such words. And in particular, Burns and Medvedev proved that for any word W implying virtual nilpotency, there exist integers E and C depending only on W, such that if W is a law in a finite group G, then G to the E, that is the subgroup generated by all E's powers of elements from G, is nilpotent of class at most C. And our next theorem provides a probabilistic variation of this result. We proved that if W is a group word implying virtual nilpotency, and if the verbal subgroup of G has high commuting probability in G, then there is a bounded integer E, bounded integers E and C, such that the subgroup generated by all E's powers of elements from G is nilpotent of class at most C. The difference here, if we compare with this with the result of Burns and Medvedev, is that, of course, that number E here depends on the probability. We cannot just say that it depends on W only. So how we prove it? The proposition tells us that there are normal subgroups. By the way, here, of course, in this case, K is a normal subgroup. So whatever I said about the case where K is normal applies in this situation. So the proposition tells us that there are normal subgroups, T in G and B in K, such that the index of T in J and B in K and the order of the commutator subgroup, T and B, are bounded in terms of epsilon only. Moreover, we already remarked that T can be chosen in such way that it intersects K by the third term of the upper central series of T. And it follows that the corresponding verbal subgroup of T is contained in the third term of the upper central series of T. Why? Well, because it's obvious that the verbal subgroup of T is inside the verbal subgroup of G, which is K. So we get this containment, and since W is a law in this quotient T over center, it follows from Burns-Medvedev theorem that there are bounded numbers I and C, with the property that the subgroup generated by I's powers of elements from T is nilpotent of class at most C. But since T itself is of bounded index in G, it also follows that there is a still bounded number E, such that every E's powers of an element of G is I's power of an element of T. And hence, the result follows. Okay, but also I would like to mention about another probabilistic nilpotency, which is quite popular nowadays. Given a group G, a finite group G, write D sub K of G for the probability that K plus 1 randomly chosen elements of G satisfies the condition that the long commutator is trivial. Here, when we write such a long commutator, we always mean left norm commutator. Then D sub 1 of G is just the usual commuting probability, as we mentioned it. In general, we have such a obvious formula for how to compute it, but it's a mystery what is the structure of finite groups with given parameter D sub k of G. Actually, if we know the number of generators for the group G, then we have very satisfying result due to Shalev, who proved that if G is a finite M generator group in which D sub k is at least epsilon, then G has a nilpotent subgroup H of class at most K, whose index is bounded. But this sheds no light on the structure of G if there is no information on the number of generators. And it's clear that this result wouldn't be satisfying if we really try to omit M from this expression. In fact, at least it's clear that any structure theorem about such groups must also include bounded by class K by bounded groups. But actually, even this wouldn't be enough, because we recently had a joint work with Sean Eberhardt, and we handled groups that are probabilistically nilpotent of class 2. And our result was somewhat surprising. If D sub 2 of G is at least epsilon for some positive number epsilon, then G has a subgroup H of nilpotency class at most 4, such that the index of H in G and the order of the fourth term of the lower central series of H are bounded in terms of epsilon only. Just the group G here must be bounded by class 3 by bounded. And by examples, we show that G doesn't have to be bounded by class 2 by bounded, as would be most natural thing to expect, and not even class 3 by bounded. So in general, we have an outstanding problem about what is the structure of groups in which G sub k is bounded away from 0. Okay, but we move on. We also considered finite groups in which a Silov subgroup has high commuting probability. The result is that if P is a Silov P subgroup of a finite group G, such that the commuting probability of P in G is at least epsilon, then G has a class 2 nilpotent normal subgroup L, such that both the index of L and P and the order of the commutator subgroup of L are bounded. Here I should mention that since L is a normal P subgroup of G, it follows that it's contained in every Silov subgroup. So in particular, L is contained in P, so it makes sense to talk about index of L in P. Okay, and so this shows that the P structure of a finite group is pretty much determined by the commuting probability of the Silov subgroup. But the situation is even more interesting if we have information on the commuting probability of all Silov subgroups in G. And actually, the result is as strong as in Peter Neumann's theorem. So the result is that if G is a finite group in which the commuting probability of every Silov subgroup is at least epsilon, then G has a class 2 nilpotent normal subgroup R, such that both the index of R in G and the order of its derived group are bounded in terms of epsilon only. So this means that under these assumptions, the group G is bounded by abelian by bounded, exactly like it was in Peter Neumann's theorem. So the idea of the proof is, well, we use the previous theorem, of course. So first, for each prime P dividing the order of the group G, we choose a Silov P subgroup S in G. And then the previous theorem says that there is a normal P subgroup L for each prime divisor P. There is a normal subgroup L of class at most 2, such that the index of L in S and the order of its derived group are bounded in terms of epsilon only. And since the bounds on the index and on the order of the commutator subgroup do not depend on P, it follows that for all big prime divisors of the order of G, this L actually must be the whole seal of subgroup, and also it must be abelian. So most of our seal of subgroups are normal and abelian. And now we consider R to be the product of all these normal nilpotent subgroup of class 2. Since they have all coprime orders, it follows that R also has also is nilpotent of class at most 2. And since most of these subgroups are actually abelian, the commutator subgroup of R is of bounded order. And again, since most of these subgroups L actually are the whole seal of subgroups, it follows that the quotient G over R have seal of subgroups of bounded order, and therefore it follows that this whole quotient is bounded. So it follows that G is bounded by abelian by bounded as required. Okay, I'd like to say now a few words about automorphisms. So if phi is an automorphism of a group G, the centralizer of phi is a subgroup formed by the elements X that are fixed by phi. So X to the phi is X. And in the case where the centralizer is trivial, the automorphism is called fixed point free. There is a famous result of John Thomson that says that a finite group admitting a fixed point free automorphism of prime order is nilpotent. This was proved by Thomson in 1859, but even before, Higman proved that for each prime P, there exists a number H depending on P, such that whenever a nilpotent group G admits a fixed point free automorphism of order P, it follows that G is nilpotent of class at most H. So combining these two results, it follows that the nilpotency class of a finite group admitting a fixed point free automorphism of order P is at most H. Now, Huchro obtained the following almost fixed point free generalization of this fact. He proved that if a finite group G admits an automorphism phi of prime order P, such that the fixed point subgroup of phi has order at most M, then G has a nilpotent subgroup of bounded nilpotency class and bounded index. So in the Higman-Thomson theorem, the group is nilpotent of bounded class. In Huchro theorem, the group is almost nilpotent of bounded class. But we obtained a probabilistic variation of this result. Just recall that an automorphism of a finite group is called coprime if the order of phi is coprime with the order of the group G. And the theorem that we proved is that if G is a finite group admitting a coprime automorphism phi of prime order P, such that the commuting probability of the centralizer in G is at least epsilon, then G has a nilpotent subgroup of bounded nilpotency class and bounded index. But before I explain about the proof of this result, I'd like to mention why I say that this is a probabilistic variation of the previous results. Let's see. In Huchro's theorem, the centralizer of phi has small order, at most M. Now, whenever you have a subgroup of small order and you pick a random element, there is a good chance that you pick the trivial element, which commutes with everything. So automatically, a subgroup of small order has high commuting probability in G. So now in our theorem, the centralizer of phi doesn't have to be of small order. Instead, we require it to have a high commuting probability in G. So that's why we say that this is a kind of generalization of the previous results. But I say kind of generalization because in this case, we really need to assume that the automorphism is coprime. If it's not coprime, I don't know if the result holds. Okay, the idea of the proof is that in the proof, we will use the well-known fact that this is precisely where we need phi to be coprime. Usually when you have an automorphism of a group and you consider a quotient by a phi invariant subgroup, your automorphism, of course, induces an automorphism of the quotient. It's important to note that in this case, in the case that we consider, the fixed points of phi in the quotients are just precisely the images of fixed points from the group G. And there will be no new fixed points. We will use this fact in the proof. So now about the proof. So let K be the centralizer. And so K has high commuting probability in G, and we need to show that G is nilpotent, has a nilpotent subgroup of bounded class and bounded index. The proposition tells us that there is a normal subgroup T in G, and the norm K in this case is not normal. So we just have a subgroup B of small index in K, and the order such that the order of the commutator subgroup of T and B, they're all bounded. Okay, here we can assume that the subgroup T is phi invariant. We just can take intersection of all images of T under phi. Okay, and then we know that N here is also of bounded order, and of course also N is phi invariant. And now let D be a centralizer of N intersect with T. So both these subgroups have a small index in G, and therefore D has a bounded index in G. And also, of course, D is phi invariant. And what's important, we also remark that B intersect with D is inside the second term of the upper central series. Why? Because N intersect with D is in the center because of this. D is contained in the centralizer of N. And if we kill the center, we just kill N, and B in the quotient B commutes with T. And since D is inside T, it follows that really B, the intersection of B with D, is in the second term of the upper central series of D. Okay, and now consider the quotient. D bar is the quotient of D by the second term of the upper central series. In a natural way, phi induces an automorphism of D bar. And then we just look at the centralizer of phi in D bar, and we know that it has bounded order because when we kill the second term of the upper central series, we also kill B. And B had a small index in the centralizer. So in this new centralizer, we just left with a few elements. Okay, so now we are in a position to use Hooke-Roe theorem and say, which implies that D bar has a nilpotent subgroup of bounded class and bounded index. And since D bar is just quotient of D by the center, it follows that also D has a nilpotent subgroup of bounded class and bounded index. That's precisely what we wanted. Okay, and even stronger conclusion can be derived about groups admitting, about groups admitting an elementary abelian coprime group of automorphism, say of order p square. So it's a non-cyclic group of order p square. The result is that if G is the final group admitting such a group of automorphism with the property that the centralizer of every non-trivial automorphism from A has high commuting probability in G, then G has a class 2 nilpotent normal subgroup R with the property that both the index of R in G and the order of its commutator subgroup are bounded in terms of epsilon and P only. So again, the conclusion here is almost the same as in Peter Neumann's theorem. The group G is bounded by abelian by bounded. So why is this? I will informally just explain. There is, first, suppose G has an A invariant seal of subgroup Q. Then the subgroup Q can be written as a product of all centralizers of the non-trivial automorphism from the group A. Now, since a random element from the centralizer commutes with a random element of G with high probability, we deduce that also random elements of Q commutes with a random element of G with high probability. Or in other words, there is some epsilon naught, depending only on the parameters that we have here, such that every A invariant seal of subgroup of G has commuting probability at least this number epsilon naught. And now we can also use the well-known fact that actually the coprime group of automorphisms always normalizes a seal of subgroup of the group G for every prime divisor of the group G. So this happens, actually this argument applies to every seal of subgroup of the group G. And now this theorem follows from our theorem on what happens when all seal of subgroups have high commuting probability. Okay. Well, there is some more stuff, but I think it's about time for me to finish. And so maybe I will finish now. Thank you.
All right. Thank you very much. Thank you, Pavel.
Who is not sleeping?
No.
Not too many people. Okay.
I'm not sleeping.
Thank you.
Are there any questions to the speaker?
Can you give an example of an open problem in this area?
Well, there was that very much open problem about this. Just a moment, I will share again. Just a moment. About this, so what can be said about, let's say, finite groups in which this parameter d sub k of G is bounded away from zero? This is very much open for finite groups, but there are also rather a lot of attempts to deal with infinite groups dealing with this. In particular, if you have a finitely generated group, you can consider balls, just words of given length, and see how often elements commute there. And there are results in this direction, and quite good results and interesting. But still, the basic question, what happens even with the finite group, which, yeah, here is this question is still open. Yeah.
Could you say a little more about what you just mentioned about infinite groups? So what kind of infinite groups is anything known about this decay, d sub k thing?
So suppose you have a finitely generated group.
Yes.
You consider balls of all elements of length at most, say, S. So you have just finitely many elements, and among these elements, you consider the probabilities that they commute. And then your S, the radius of your ball, you...
Yeah, no, I understood the setup. My question was for which groups is anything known? For which infinite groups are there any results, any substantive results, and what kind? Do you remember?
I don't know, but okay, everything that I said is rather easily can be interpreted for, say, for compact group. Compact groups, they naturally have higher measure.
Right.
So
yeah,
with
but
respect to this measure, we have probability.
Mhm.
Yeah, and about what exactly you're asking about balls, I'm not sure. I'm not sure that I don't want just to say something that I'm not sure of. But I can give you some references if you want. I can give you later
Okay.
in private communication.
Okay.
There are also some results in model theoretic interpretation of this parameter, and there whereas some definable subgroups are called something, and then we have a measure with respect to these specific subgroups. There are results. There are actually rather a lot of activity about these problems.
Okay. Any other questions? So actually, it's something that I wanted to ask. I don't know whether it slightly escaped my memory. I don't know much about finite groups, but one of the things that I've seen is where people study this, what do they call them? Word measures, on finite groups, where you have a finite group G and then a word in several variables, let's say in K variables.
Yes, there is also this.
And so you sort of push forward the uniform probability measure on G to the K and to G, and you study like the random value, right, of this word. And one can do it, for instance, with the with the commutator of K elements. And one of the things that I've seen is that people study, although I've only seen it in the context of the symmetric group, of finite symmetric groups and their subgroups, where people study the expected number of fixed points for this kind of random elements of the symmetric group, which come from words.
Yes, there is a lot of this. Yes,
right. And I think one other thing that one can sort of try to do is if you have like just the commutator or iterated commutator, and you have some kind of a subgroup of the symmetric group of on n symbols, then being having exactly n fixed points for an element there that corresponds to being trivial, and having a large number of fixed points, whatever that is some kind of a sense of being close to being trivial. And I don't know whether anything is known about this, the expected number of fixed points for for commutators and iterated commutators in that context.
Okay, I'm not ready to say. I know that the first person to deal with these questions was Paul Erdos. Erdos actually had this already in the 60s. But I wouldn't want to comment about this because I'm not sure and not prepared to answer this kind of questions.
Okay, thank you. Any other questions? All right, let us thank Pavel again. Thank you. So I'll stop the recording now. If I can find the record button, where is it?